Hi, everybody. This is lecture over section 9.5. Alternating series test. And you can go ahead and read these. Use the alternating series test to determine whether an infinite series converges. You could also use it to approximate the sum of an alternating series, and we're not going to be doing that. Classify a convergent series as absolutely or conditionally. And we're not going to do the second part either, rearranging. So we're not doing in this lecture or in the homework, we're not doing this or this. Yes, we are going to be doing these two. All right, alternating series. Now, alternating series goes both positive and negative. This is normally done by this negative here, or you can say -1 to the n power, whatever n is going to be. And if you notice, you put 0 in, you get 1. You put 1 in, you get -1/2. You get put 2 in. Every time you put an even number here, you get a positive value. This is n2, n4, and odd numbers that you put in there, and other than 1, even an odd number 1, you get a negative value. So this is an alternating series. It's geometric, and geometric R equals 1/2, but in this case R equals a -1/2 if we set it up like this. They wanted to show you that this can be broken into 2 pieces. And from now on, we're going to call this part, that part that doesn't have the sign changing, a sub n. All right. So the alternating series test says the a sub n part has to be positive. And it's an alternating series, like we said. The limit of just the a sub n part has to be 0. And each successive a sub n term needs to be lower. Do you see a sub n, a sub 2 has to be lower or smaller than a sub 1. So each next test will be lower in value when we're just looking at the a sub n. So the a sub n limit has to approach 0, and each term, successive term, has to be smaller than the previous when we're just looking at the a sub n. Determine whether this series converges or diverges. So if we look here, if we just look at this series here, just the a sub n, that's the a sub n. If we just look, and we're going to take the limit of this 1 over n to infinity, and you see the limit approaches 0. 1 over infinity equals 0. Also, you can look at each test. If I do n2, I get 1 over 2. If I do n3, I get 1 over 3. This is n plus 1. If this is n, you see if I put a 2 in here and I put a 3 in here, you can see that the n plus 1 is smaller than the n itself. So it is decreasing. this limit of this a sub n is 0, so the whole thing converges. So the 1 over n converges, so the alternating series converges also. Once again, the successive term is smaller than the previous term. And since this converges, then the whole alternating series converges. Okay, so, and then, I mean, that's pretty simple. Well, let's put it this way, it's clear cut, as long as you know the P series or geometric series. You know about those because we'll be using those over and over again. Now, absolute and conditional convergence. What happens if your alternating series looks good, but your a sub n itself doesn't converge? So occasionally, a series may both have positive and negative terms, but they're not actually alternating series. So let's take a look at the convergence of this series here. And you can plug these numbers in and verify that the sign does change from time to time. So to be absolutely convergent, for a series to be absolutely convergent, the summation of a sub n converges, and then the entire series converges. So if we look at this particular problem, this is an alternating series. You see it goes positive, negative, positive, negative. So it is alternating. We look at this. If you look at this, this is the same thing as -1 to the n and 1 over n. So this is our a sub n part. And they're going to show you once again absolute convergence when the summation of a sub n converges, conditional convergent when the summation converges, but the whole thing diverges. The whole absolute value part diverges. And we'll show you some examples of that here. Let's look at A first. If you look at n factorial, just the a sub n part, as you move further along, let's plug some numbers in just to show you. Plug in 1 and you get 1 factorial over 2 to the 1 power. Plug in 2, 2 factorial is 2 2 squared is 4. So you also get 1/2. Plug in 3. 3 factorial is 6. 2 to the 3rd power is 8. Plug in 4. 4 factorial is 24. 2 to the 4th power is 16. Do you see this goes from 1/2, 1/2, 3/4, 24 over 16. They both divide by 8. 4 over 8, 3 over 4. 8, 4. Sorry. They both divide by 8, which is 3 over 2. Sorry. There we go. Do you see how this doesn't approach 0? It doesn't approach 0. It's getting larger and larger. The alternating series, it doesn't approach 0. Or just looking at a sub n, it does not approach 0. So if just by the alternating series test, we can say that A diverges. Now the second one. The second one is, once again, the a sub n is the 1 over the square root of n. The other part is the alternating part. We want to look at this part. 1 over the square root of n is n to the 1/2. And that's the p series. P is between, if you remember, P is between 0 and 1. Then this part diverges. The a sub n part diverges. However, the alternating series part, this is getting smaller and smaller. Each successive number, you plug 1 in there, you plug 2 in there, you plug 3 in there, you plug 4 in there. Each is getting smaller. Each of these is getting smaller. So it does converge. The alternating series part passes. So the giving series shown is convergent by the alternating series test. Do you see the alternating series part is converging? It passes those two tests. But the p series part, the 1 over n to the 1/2, the p series part, the a sub n part diverges. So if you have the alternating series converge and the p series, the a sub n part diverge, then we say this conditionally converges. It doesn't absolute. Absolute converges is if the alternating series and the a sub n both converge. But since the a sub n does not converge, but the alternating series passes their convergence test, it's conditionally convergent. And once again, the best way of looking at that is going back up to the rules that we've looked at. The a sub n has to approach 0. Ours does not approach 0. Each successive term has to be larger. Each successive term, has to be smaller, but ours was larger. Because of the p series test diverges, then the a sub n diverges. You they're showing if this converges when they both converge conditionally. if one of them don't converge. Let's take a look at the homework. If I can find it. All right. So when we look at this first problem, if you notice, it's the same thing as looking at the a sub n part is 1 over n plus 8. And we can do the comparison test. This is the same as 1 over n using the comparison test. And so let's look at successive terms. Once again, if I put n equals 2 in here, I get 1 over 10. Put n in 2. And then if you go 1 over n plus 1 plus the 8, when you put 2 in there, you get 1 over 11. And it gets smaller. The n plus 1 gets smaller from the 10. So we're okay there. That's what we wanted to verify, that the next n is smaller than the previous n. Now, if I look at just the n then, 1 over n plus 8 and 1 over n, and don't forget when we can do the comparison test, as the limit n approaches infinity, this approaches 0. So according to the alternating series test, if each successive value becomes smaller and the limit of our a sub n approaches 0, and by the comparison test, this converges to 0, this also converges to 0. So using the comparison test, so then the whole thing converges. That's a little tricky. If you notice, once again, the limit comparison test, not the limit comparison test, the alternating series test says the a sub n has to have a limit of 0. Well, our a sub n is 8n minus 1 over 5n minus 1. If you look at this, these are the n's with the same power. So we can say this limit approaches 8 over 5. Since the limit does not approach 0, the limit does not approach 0, we can say this diverges. Once again, if you go back to the at the very beginning of the alternating series test, at the very beginning, I think I was just there. The limit of the a sub n has to approach 0 for the alternate series test to be convergent. And then each successive term has to be smaller than the previous one. And that's theorem 914 in the book. So let's take a look at this one really quick because it's kind of cool. In the help, I mean, when you just look at this problem, it has trig in it. It's a little confusing, but they're showing you that this is the alternating part. This cosine of n times pi. If you look at a unit circle, wherever one is for me, and you're looking at pi and cosine, you see at cosine 0 or 2 pi, cosine is 1, but at pi, it's -1. So it alternates there. The cosine of pi times n, there, if you put a 1 in there, it's cosine of pi, which is a -1. If you put a cosine of 2 pi, you get a +1. Cosine of 3 pi, you get a -1, and so on and so on. So this becomes this series here, the alternating series with 1 over n. Since 1 over n we know converges to 0 when the limit of n approaches infinity, 1 over infinity becomes 0. Okay, in question 5, if we look at this, the alternating series test, if you look at that, each number gets smaller and smaller as the n's increase. So that passes. If you take the limit as x approaches infinity, this approaches 0. However, if we just look at 1 over 8 to the n, this is a geometric series where r equals 1 over 8. And geometric series, if r is less than 1, then it converges. So this converges, and so does the alternating series. So the whole thing absolutely converges. So the whole thing absolutely converges. Now, question 6 is a little different. Each successive term this is the same thing as 1 over n. This is a p series where in this case, p is right here, p equals 1. And if you remember from p series, if p is between 0 and 1, the whole series diverges. So this part does converge. This part diverges using the p-series test. So the whole thing conditionally. So if the top part converges, the alternating series part converges, but the p-series part of this test diverges, then we say it conditionally converges. And we could look at the same thing down here. you can look at it once again. I like to set it up like this. 1 over the square root of n plus 8, which if you do the comparison test, it's 1 over the square root of n, which is the same thing, 1 over n to the 1/2. And once again, P series test, that's the P part. P equals 1/2. So this part diverges because P is between 0 and 1. If P is between 0 and 1, the whole thing diverges here. So we said this converges, and it gets smaller and smaller as you increase n. So this part passes, but this part does not. So once again, we say conditionally converges conditionally. All right, I hope that helped out in the homework.